In this video, we're going to make sense of polar bonds, nonpolar bonds, ionic bonds, covalent bonds, and kind of make sense of all that terminology and really try to understand what it means, because it does have good meaning to it. And to do so, I'm going to tell you about three sets of three sisters. And the story goes like this. There is an older sister who graduated college and got her first job. And so she was making more money than she had ever made before. And so she bestowed her car in college that she had to her set of younger twin sisters. And so this is a nice picture of her car. And who wouldn't want that ride? You can see why I didn't become an artist. So her twin younger sisters are in high school, and they got this car from their older sister to share. And her two younger sisters were going to share the car. Her two younger sisters' names were Cammie and Camille. And so Cammie and Camille were going to share the car, and over the course of 1 year, they tallied up the amount of days that each of them got to use the car. And it turned out that Cammie got to use the car 6 months out of the year, and Camille got to use the car 6 months out of the year. So, in essence, Cammie and Camille shared the car in time and for an equal amount of time. They shared it perfectly. It was a perfect sharing of the vehicle. It was 50% of the time Camille had the car and 50% of the time Cammie had the car. Well, in a town, a couple towns away from where Cammie and Camille lived, there was another scenario of three sisters in the exact same position. And this time, showing only the twins. Whoops. This time, Heidi and Olivia were the twin sisters. Unlike Cammie and Camille, Heidi, when you added up the amount of time she got the car for what equated to about 3 months out of the year, where Olivia got to use the car about 9 months of the time throughout the year. And so Olivia definitely had the car more than Heidi did. And in a final scenario, 2 towns away from where Heidi and Olivia lived, Bernadette and Faith were the 2 sisters sharing the vehicle. Bernadette had the car for about half a month, and Faith had the car for about 11.5 months throughout the year. Pretty much this was Faith's car. I mean, Bernadette really didn't even have the car. Faith had the car. And so these 3 scenarios really sets the stage for understanding bonds. So let's talk about the 3 bonds that we essentially described in a story. In the first one, Camille and Cammie, C and C is abbreviated here, were sharing the car. They shared the car equally. In fact, this bond right here that we see really is indicative of 2 electrons. Whenever you see that bond between 2 atoms like that, that's indicating that there's a bond there, and that bond is being shared between the 2 atoms. And that bond is representative of 2 electrons. And of course, electrons have a negative charge on them. In our second example, Heidi and Olivia were sharing a car, right? And again, we still have a bond in between Heidi, which will represent as an H, and Olivia, which will represent as an O. That bond is still 2 electrons. And again, electrons are negatively charged. In our third example, we had Bernadette, which I'll abbreviate as BE, and Faith also were sharing electrons. But in this case, we're going to see that this was not really equal sharing of electrons, so I'm going to remove that bond because really they weren't sharing it, right? We decided that Faith pretty much had the car. And so Faith pretty much had the car the entire time, and Bernadette really didn't get the car very often. What I need you to do for our next part is pull up an electronegativity chart. You can find an electronegativity chart if you go online and you can just type in electronegativity chart and you'll see one. Or you can get a chemistry book. It'll have an electronegativity chart in there. So take a moment, get that out because we're going to look at the electronegativity chart. The electronegativity chart looks like a periodic table, but the information within it is a little bit different. So now let's get a little bit more into bonds. Covalent bonds, ionic bonds, polar bonds, nonpolar bonds. And what this all really represents, all those terms, when you're talking about bonding, you're really talking about how well are the two atoms sharing the electrons, much like how well were the sisters sharing the car. And we don't have to guess as to how well they're sharing it. We just have to do a little bit of mathematical calculation and very simple math. If you look at your electronegativity chart, you'll notice that each atom has a number associated with it. And we're going to look at that. So look at your periodic table and let's take a look at C, or carbon. If you go find carbon on the electronegativity chart, there's a number associated with it, and that number is 2.5. So I'll write that under carbon as 2.5. Because this C as well is 2.5, you'll notice that they are the same number, obviously, because they're both carbons. Now, the meaning of the actual number 2.5 really doesn't have much. It has some meaning, but really, for our sake in this conversation, really has no meaning to it. What we're interested in is the difference between the two numbers of the atom. So notice we have a 2.5 under this carbon and a 2.5 under the other carbon. If we subtract those, you'll see we get a 0 value. And that's important. Let's look at our next comparison, our next bond for a moment. Let's look up hydrogen. So look up hydrogen on the electronegativity chart and look up oxygen on the electronegativity chart and find the value associated with each of those atoms. You can pause the video and find that, and when you come back, I'll talk about the answer to that. So hydrogen on the electronegative chart is 2.1, and oxygen is 3.5. So oxygen has a higher value than hydrogen. And we can again calculate the difference between those two numbers, and we don't do negatives here, we just make the number positive. So I'm going to do 3.5 minus 2.1. I can put that into a calculator, or I can put that into my head and figure it out, and I get a 1.4. So that number there, 1.4, is very different than the carbon-carbon comparison that when we got 0. We'll also go on to the last one here. Let's look at a bond between beryllium and fluorine. And so we see here beryllium, and again, you can pause the video if you'd like and find the numbers for yourself and do the calculation. And I'll wait here for just a moment, and then I will pick back up where I left off. So beryllium, I have on my chart, is a 1.5, and a fluorine is 4.0. Again, I'm not too interested in getting negative numbers here. We just want the absolute value of that difference. So we subtract 4.0 from 1.5, and I get 2.5. Awesome. So there's the three values I have for each of these. So what do these values represent? Well, there's a little, the numbers, the difference between the two atoms tells you something about the bond that is occurring between them. When you get a number like 0, like we have here, this would indicate a covalent bond, and it's nonpolar. The second one here, where we got 1.4 between the hydrogen and oxygen, that is also a covalent bond, and it is polar. And the third one here is an ionic bond. And so those values actually tell you what type of bond it is. And I'll give you some values or some ranges as to how you figure that out. But let me just talk about what this really means. So if you look at the covalent nonpolar bond, what it means is that those two carbons, because it is a covalent nonpolar bond, it means it's sharing those electrons basically evenly. It's perfectly sharing those electrons. Each carbon is getting those electrons about half the time, and so it's a perfect sharing of those electrons. In the second example, the hydrogen and oxygen, it's not a perfect sharing. Remember, Heidi didn't get the car very often compared to Olivia. In this case, the same scenario, where in this case, the electrons are spending more time with O than they are with H. And so because they're doing that, it creates a polar bond, meaning because the electrons are hanging around the oxygen more often than the hydrogen, oxygen, because of those electrons and they're negatively charged, carries a partial negative charge. And that's a Greek delta symbol I just drew on there with a negative next to it, meaning the Greek delta symbol there means partially, and so it's partially negative. Where the hydrogen is partially positive because the electrons, the negative charged electrons, are more often around the oxygen. That leaves that hydrogen a little bit positive. They're still sharing the electrons, it's just not an equal sharing of electrons. Remember, Olivia had it for 9 months of the year and Heidi only 3. So yes, they are sharing it, just not equal. Where a nonpolar bond is an equal sharing. So each of those carbon atoms don't have any extra negative or positive charge associated with them. They're pretty neutral. If you look at the last example, an ionic bond, in this case, notice the fluorine will not be partially negative, it'll be fully negative. And the beryllium will be fully positive. Why? Because pretty much of the electrons are spending all of their time with fluorine. And so therefore, all those extra electrons give the fluorine a little bit of give it a strong negative charge. And because the electrons aren't hanging around beryllium, beryllium tends to be positive. And so this is an ionic bond. An ionic bond is really kind of a sharing of electrons, but the sharing is so unequal, we just call it an ionic bond. The ionic bond, you probably, if you've heard of any of them before, is Na plus Cl minus. And there again, that's an ionic bond where the electrons are spending all their time around the chlorine atom, not the sodium atom. And so it's an unequal share. It's a very unequal sharing. So unequal, it's basically the chlorine has the electrons or the fluorine has those electrons, and they have them all the time. Going back to the numbers associated with on the electronegativity chart, notice what they do tell us. Notice the bigger the number, or the larger numbered atom, is the one that's going to have the electrons more. So when you have an unequal sharing of electrons, the larger one's the one that's getting the electrons. So that's what that number tells you. The number tells you not only, it helps you calculate the difference between the atoms, but it also helps you determine which of the atoms gets the electrons. And so notice the hydrogen was 2.1, the oxygen was 3.5, so the oxygen got the electrons because it was the bigger number. And the same scenario with the beryllium and the fluorine. The fluorine has the larger electronegativity number, so therefore when compared to the beryllium, the fluorine is the one that's going to have the electrons associated with it. Now, how do you know based on the difference which one it is? If the value on your subtraction is between 0 and 0.4, this is a covalent bond, which means we're sharing electrons, and it's nonpolar, means that we're not only sharing them, but we're sharing them pretty much equally. They're pretty much getting the same amount. If the difference is from 0.5 to about 1.6, and books differ on this value. I like this value. I think this one works better, especially when you get into organic chemistry. It is also a covalent bond. We still consider that sharing electrons, but it's not equal sharing. It's weighted one way towards one atom versus another. So because it's unequal sharing, it creates a polar covalent bond. And remember, when you have a polar covalent bond, one of the atoms is going to be partially negatively charged because the electrons are hanging around that one a lot, and the other one will be partially positive charged. If it's greater than 1.6, we call that an ionic bond. When you hear the term ionic, it pretty much means we're not sharing anymore. One of the atoms is getting all the electrons pretty much all the time, and the other one's not really getting it. Doesn't mean the other one won't get it. It just means that most of the time, 11.5 months out of the year, it's going to be with one atom, and maybe a couple days of the year it'll be with the other one. So very unequal sharing. So unequal in the sharing, we just say the other one of them pretty much has the electrons all the time. In our case, Faith had the electrons, or the car, all the time, and Bernadette really didn't get the car ever. And so in that case, is that really sharing? In science nomenclature, no, it's not. We just call that now an ionic bond. So what I'll do now is I'll give you a couple to try on your own, just a couple of examples if you'd like to try them. And then pause the video when I give them to you, calculate the difference, and determine whether they are covalent nonpolar, covalent polar, or ionic. So let me give you those. I'll put those examples up here on the screen in just a moment. Okay, so here's 4 examples. If you want to pause the video, determine whether they're non-covalent or nonpolar covalent, polar covalent, or ionic. And then restart the video and I'll give you the answer. Okay, so for the first one, carbon is 2.1, or 2.5, sorry. 2.5, and hydrogen's 2.1. The difference between them is 0.4, and so this would be a nonpolar covalent bond. Okay, so what that means is the carbon and hydrogen in a bond pretty much share the electrons equally. NaCl, the Na is 0.9. The Cl is 3.0. And the difference between those is 2.1. And 2.1 on our chart is definitely greater than 1.6. And so this would be an ionic bond. The next one, the third example, the carbon is 2.5. And the chlorine is 3.0. And so the difference between those is 0.5. That falls in the range of 0.5 to 1.6. So that makes this a polar covalent bond. Sorry about my writing. This pen is difficult to use sometimes. And the last one, the sulfur and hydrogen. On the sulfur, on my electronegativity chart, I see sulfur has a 2.5 and a hydrogen has a 2.1. And so the difference there is 0.4. And so this would fall into the nonpolar covalent bond. And what that means is, again, the sulfur and hydrogen will share the electrons pretty well evenly, where the carbon and the chloride, seen in example 3, or number 3 there, not quite equal sharing, and so we actually think that's enough to where the electrons will be unequally shared. Who's getting more of the electrons? The chlorine is. It has the higher number. Its number is 3.0. Carbon's is only 2.5. So chlorine will get the partial negative, and the carbon will get the partial positive in that case. In the sodium chloride, number 2, again, unequal sharing. Chlorine, because it's unequal in its ionic bond, chlorine won't get a partial, won't get a partial negative charge. It'll get a full negative charge because all ionic bonds get a full negative charge and a full positive. And the sodium will get a full positive charge. And that bond in between really isn't there. That bond usually represents that there's sharing going on So in 1, 3, and 4, the bond would be that line between the two atoms would be shown because that indicates sharing, where between the sodium and chloride, there would not be a line between them because they're not sharing it. They're actually, each chlorine's getting the electrons and sodium is not getting the electrons. Well, I hope this helped you. Please check out some of the other videos if you like this. If you have any suggestions for future videos, I'd be happy to post some.